STP Gases Intro. What is STP? It's standard temperature and pressure. Well, what are those temperatures and pressures? It's 1 atmosphere of pressure, which is also 760 torr, which I'll explain later, and it's 0 degrees Celsius, which is also 273 degrees Kelvin, which is what we're going to have to use for these problems because Celsius doesn't work. I'll explain this all in a bit. Don't freak out. Kelvin is 273 degrees bigger than whatever Celsius is. Also, we're going to learn that any gas at STP will occupy 22.4 liters. As a matter of fact, I know we discussed that before. So if you had 50 grams of nitrogen, and we're supposed to know that nitrogen is a diatomic gas, so we know it's N2, the molar mass would be 28 grams per mole. 50 divided by 28 is that many moles. And that many moles times 22.4 liters per mole would give me 40 liters. And the moles cancel out. On number 2, I have 100 grams. Oxygen we're supposed to know is a diatomic gas, so it's O2. The molar mass of O2 is 32 grams. When we convert to moles, we do 100 divided by 32. We get this many moles. But on number 2, it says the combined gases, right? Because we added the oxygen to the nitrogen, so the moles add up. And this is the total moles of gas now. And another one of our little theories of science is that pretty much every gas molecule is about the same size as every other gas molecule. And while the extra picky of you may say, well, no, it's not, that can't be true. Okay, to be really picky, you're right. But compared to the space between them, it doesn't matter. The space between them is so much bigger than the gas molecules themselves that we get a good enough answer if we just treat them like they're all the same size and they take up all the same space. So I can use this 22.4 liters per mole for even for the situation when these are different gases added up. So we'll just count this as moles of total gas, and we'll multiply by 22.4 liters per mole and get 110 liters. On number 3, if I had this many moles of CO2, I can convert to grams, and this many, 1 mole would also be this many liters. Okay, because what were we asked for? The density, grams per liter. So what did I need? I needed grams. Oh, look, I got grams. I needed liters. Oh, I got liters. If I take these two numbers over each other, my unit will be grams per liter, which is what I wanted. So I'll take the grams that I got over here, or the liters that I got over here, and I'll get grams per liter. Okay, for number 4, let's tell a little story, so to speak, because it looks like we're being weird, and one of the things I remember saying to myself is, that's dumb. You can't measure pressure in a distance, like millimeters, because no one told me the story of the first barometer. So there was an Italian scientist who invented the barometer, which is the air pressure measuring device, and he was very clever, and he had nothing like we would call technology. But this is what he did. He took a little dish, filled it with mercury. That's the atomic symbol for mercury. And he took a closed tube. This end is closed on this tube. This end is open. Filled it with mercury, because he probably didn't know that mercury can be a little dangerous, or a lot if you're breathing it and so forth. And I know you're going to say, you can't breathe a liquid. Well, it evaporates a little too, so that can be bad. He probably put his thumb over it and just took the tube and turned it over and set it in the dish. So now the mercury, because of gravity, tries to fall down. But here's the other thing he realized. The air pressure is pushing on the mercury in the dish and trying to push the mercury up the tube. So gravity is trying to pull it down, and the air pressure is pushing it up. Well, gravity is not going to change. So the only reason this mercury would go up and down the tube a little bit is because the air pressure changes. And so what's been discovered is that on a standard day, whatever that means, but a standard day, I guess the average day, where the pressure is 1 standard atmosphere, that's not ATM like where you get cash, that's atmosphere, 1 atmosphere. the mercury will be 760 millimeters up the tube. So these are both the same thing. 760 millimeters and 1 atmosphere mean the same thing. They mean a standard day of air pressure, but 760 millimeters is the distance of the mercury up the tube. And the reason you don't use something nice and cheap and easy like water is because then you get into something like 3 stories high. And it's a pain in the butt to measure. So, I told you his name was Torricelli, and he has been honored with calling 1 millimeter of mercury of air pressure 1 torr. And we just said 760 torr is 1 atmosphere. These are the same thing, kind of like 12 inches is a foot. And another one I got to throw in here is 101.3 kilopascals, which makes a lot more sense if you're in physics class, because it's harder to just change the units around in physics class for reasons I won't get into here. But these are all really the same thing, just in different units. Just like you could have a foot that's measured in meters, and it's still the same length, right? It's still the same length of object, even though you measured it in meters. You could call it a foot, or you could call it whatever meters. So, here's our combined gas law or formula. If you take a gas and you have a pressure of the first situation, and a volume of the first situation, and a temperature of the first situation, this times this divided by that will be equal to the new pressure times the new volume divided by the new temperature. So on number 4, they give us some information. And remember, millimeters of mercury is torr, so that's 900 torr that they tell us. They tell us 300 K. They don't tell us 300 K, they tell us 27 Celsius. Okay, I got to go over here. Let's talk about Celsius and Kelvin. So, you've probably heard of places being negative degrees, and in America they usually mean negative degrees Fahrenheit. Well, Fahrenheit doesn't really work very well in science, and we're about the only country who uses it at all. And in science we use Celsius. However, Celsius has a big drawback. Mr. Celsius, there really was one, designed the thermometer so that 0 degrees Celsius is the freezing point of water at normal conditions, and 100 Celsius is boiling of water at normal conditions. But that leaves out a whole bunch, because is there such a thing as negative Celsius? Sure there is. And what we mean is that the molecules are getting vibrating less and less and less, and less and less and less, and less and less and less, but they don't stop until they get down here. But that's negative 273 Celsius. Well, that doesn't work very well for us, because if you put negative numbers into calculations, you can get stuff like negative volume, which doesn't make any sense, and negative pressure, which doesn't make any sense. So this number is pretty useless. Plus, if you go from, say, like 5 Celsius to 10 Celsius, and you leave it like that, your math looks like the amount of energy, because that's what temperature is measuring, is energy. It looks like the amount of energy has doubled because you went from 5 to 10. But I think you can agree that if you really think about it, the energy hasn't doubled just going from 5 to 10. I mean, look how little the jump that would be, right? It'd be just like this. So that's not true. So what we're going to have to use is a scale developed by Lord Kelvin. That's why it's called Kelvin. And it starts at absolute 0. No motion of molecules is 0 Kelvin. So, if you go from, say, 100 to 200 Kelvin, you really did double the energy, and that is true. So when we use the temperature in these formulas, we're going to have to use Kelvin, and Kelvin is 273 degrees bigger than whatever Celsius was. So this is negative 273, or 0. 0 is 273, and 100 is 373 Kelvin. So just add 273 to get to Kelvin, subtract 273 to get to Celsius. So, back here, I added 273 to my temperature, and I got 300 Kelvin. What's the question? What's the new temperature? The pressure, new pressure. And the temperature drops to negative 183 Celsius. So I added 273 to negative 183, and I got positive 90. So the new temperature is positive 90 Kelvin. You'll notice that I crossed out volume. Well, that's for, I could explain that a couple ways. It's using an air tank. Does the air tank volume change? Of course not. So if I have any number that doesn't change across here, it will just cancel out. So it doesn't matter if I know what it is. It just matters that I know that it doesn't change. If it doesn't change, I can just say, well, it would have crossed out, and I can skip it. There's no point in putting it in just to cross it out, so let's just skip it in the beginning. To solve for P2, we're going to take 900 divided by 300, and the 90 moves up and over, and we multiply. So it's 900 divided by 300 times 90 Kelvin. And you know what? That is wrong. It's not Kelvin, is it? It's torr.